Hello. In this video, I'm going to talk to you about orbital hybridization. Orbital hybridization is a really fundamental part of bonding theory. And it turns out it's a little bit different from what we teach you in high school. So at some point, someone hopefully told you that the top row of the periodic table has 2 electrons and that they had a single valence shell. So you had an atom and 2 electrons in a spherical orbital around them. And then we learned that in the next row down, so this is called the 1s2, because it's the first inner shell, and then it has 2 electrons in it. And one down from that has now a second shell, and that shell contains 8 electrons. So it has a 2s2, a 2px2, 2py2, and 2pz2, where the 2's mean they're in the second shell, and the little 2 means there's 2 electrons, and then each of these are directional. So the s orbitals, just like here, are spherical and surround the nucleus. And then these p orbitals are all shaped like this, and they're arrayed either in the x direction, the y direction, or the z direction. And so we could build the rest of our model of our atom like this, okay? And so this is fine. This is a good way to think about atomic structure while you're learning about it. But once we get to organic compounds, we find that this breaks down, okay? This particular model does not correctly predict the bonding that we actually see in organic molecules. Okay, so what we actually see for, say, a carbon atom, which is in the second row, when it has 4 things attached to it, they're not at 90 degrees to each other. They're at 109 degrees to each other. 109.5 if we're going to be specific. Okay, and this is something that we explain using VSEPR theory, valence electron shell repulsion theory, which basically says that because electrons are negatively charged, they want to get as far apart from each other as possible. Now we can't get to 109.5 degrees using just these orbitals, and so VSEPR theory utilizes a hybridization of orbitals. It says that instead of just these, they're actually mixed together to reform orbitals that are directional in the way that we see in the real world. So let's take just a second and watch a video so that I can show you in a computer rendering what these atomic orbitals actually look like and then how they hybridize to these molecular orbitals. And then we'll talk about the actual skills that I want you to have, okay? So how to look at a carbon or any other atom and tell its hybridization, and then what that hybridization should tell you about the bonding and the bond angles for that compound. So these are the orbitals that we're going to be hybridizing. We have an s orbital, which is the red ball. Okay, it's spherical. And then the other 3 are the p orbitals. So they have 2 lobes, okay, and they're oriented in either the x or the y or the z direction. Now all of the atoms have access, they have all of these orbitals. Depending on how many bonds they're making, that's going to decide how many of the orbitals they need to hybridize in order to make that many bonds. The number of atomic orbitals that we start with is going to be the same as the number of molecular orbitals that we make. So if we have a carbon that's making 4 bonds, okay, a standard tetrahedral carbon, then that carbon is going to need to hybridize all 4 of these bonds, 1s and all 3 p's, to make the sp3 hybridized orbitals. And that looks like this. These are sp3 hybridized. All of the orbitals are 109.5 degrees apart. Okay, they're as far apart from each other as they can get in 3 dimensions. Again, this is because these are all electron clouds, and the electrons want to get as far away from each other as possible. And so when we hybridize all four, the 1s and all 3 p's, we get 4 directional orbits, and they are tetrahedral with a bond angle of 109.5. Now if that atom, that carbon, only needed to make 3 bonds, then it would be sp2 hybridized. So this is the sp2 hybridized orbitals. Okay, so if it used 1 s and 2 p's, then it would make 3 molecular orbitals. They're all in the plane, okay, and they're 120 degrees apart. So this angle is 120 degrees. That's the farthest away that we can get 3 bonds. Now that carbon still has the unhybridized p orbital. Okay, that carbon always had 1s and 3 p's. If it's only using 2 of the p's to make the sp2 hybridized orbitals, then the unhybridized p orbital is still present, and it lives at 90 degrees to the sp2 hybridized plane. Okay, so if we look at it from the top, there we go. All the sp2 hybridized atoms are 120 degrees apart, and the unhybridized p orbital is at 90 degrees to those. Now if the carbon only wanted to make 2 bonds, then it would be sp hybridized. It would use 1 of its s and 1 of its p's, and what you would get is actually 2 molecular orbitals. Now I know there's 3 here, and that's because they can be directional. Okay, so if it was hybridizing the px, then the sp hybridized orbit would look like this, and there would just be 2 of them. Okay, one would be faced like this, and then one would be faced like this. If it hybridized the py, then it would be directional in this direction, and if it hybridized the pz, then it would be oriented in this direction. Okay, so we're using 2 now, and what we get is a directional orbit only in one of these planes, either the x or the y or the z. And that means that if you're sp hybridized, then because they're directional, everything can be 180 degrees apart. Okay, so 180 degrees is as far away as you can get 2 things in a plane. And so sp hybridized bond angles are 180 degrees. Okay, they're straight because these hybridized orbitals are directional with respect to the plane. Okay, so now we've watched that video and you can see what those orbitals look like. Let's talk about how to actually figure out what the hybridization is. So I'll give us a molecule to practice with. Okay, so this contains carbons at a lot of different hybridizations, which we're going to talk about now. So let's start with this carbon. This carbon has 3 hydrogens on it. Okay, which means that it has 4 things bound to it. 1, 2, 3, and then this carbon. So that's 4 different things. So this carbon, like every other atom, has 1 s and 3 p orbitals at its disposal. And however many bonds it's going to make, that's how many orbitals it needs. Okay, there's something that requires us to have the same number of orbitals, atomic orbitals, as molecular orbitals. And so if we're going to make 4 bonds, then we're going to have to mix all of these together. And when we do that, we get something that we write like this. Okay, we're using 1 s, S1, and 3 p's, P3. Now, because we're lazy and it makes it a little messy, we typically don't draw this 1. You'll usually see this drawn just as sp3. And we're assuming that there's a 1 here, but we don't typically draw it. And so if I'm going to make 4 bonds, I need to mix all of my atomic orbitals. That makes it sp3. And so we would label the hybridization of this carbon as sp3. Now sp3 hybridized atoms have their bond angles at 109.5 degrees. That's the bond angle that gets them as far away from each other as possible. So now let's move to this carbon. There's one hydrogen here, which means that this carbon is bound to one carbon, two carbons, and a hydrogen. 3 different atoms, okay? 3 different things. It still has 4 bonds. It has 8 electrons, okay? 2, 4, 6, 8. But it's only bound to 3 different things. And if we have 3 different atoms that were bound, okay, so this carbon has 1 s and 3 p orbitals to work with. If we need to make 3 bonds, then we need to hybridize 3 of these orbitals, 1 s and 2 p's. And so we draw that like this, sp2. It still has this unhybridized p orbital, okay, and we'll learn that where that orbital is this pi bond. Okay, the double bond here is being made by this unhybridized p orbital. Okay, and so because this carbon is sp2 hybridized, that means that its bond angles are 120 degrees. That's as far apart as we can get 3 things so that their electrons have as much space around them as possible, 120 degrees. And so practically that means that this angle is 120 degrees. Okay? The last one I'm going to show you on this example is this carbon. Okay? These 2 are the same, but we'll just use that one. This carbon has 2 things bound to it, a carbon and a hydrogen. It also has 1 s and 3 p orbitals. It's making 2 bonds, okay? 2 different things are attached, and so it's going to hybridize 1 s and 1 p. That makes it sp hybridized. Okay, so this one is sp hybridized. We don't write a number on top of either one, so they're both assumed to be 1. And if it's sp hybridized, well, then the bond angle is 180 degrees. With only 2 things attached, it can be linear. We can get the electrons literally as far apart as they can be, 180 degrees from each other. Now this carbon does still have 2 unhybridized p orbitals. And these 2 unhybridized p orbitals are making the triple bonds. Okay, one of them is making a double bond, and the other one is making a triple bond. So that's how we calculate it. The other thing I wanted to point out, if I just give us another quick example, we'll do NH2, is what to do with lone pairs. Because lone pairs are going to count as if there's something attached. So if we look at this oxygen, it has 2 things attached, okay, 2 carbons, but it also has 2 sets of lone pairs. Since we're going to count lone pairs as if that was a thing attached, this has 1, 2, 3, 4 things attached, and so it's sp3 hybridized. 1, 2, 3, and the one that we don't usually write. Okay? sp3 hybridized means bond angles of 109.5. We're going to handle the nitrogen's lone pair the same way. This nitrogen has 1 carbon bound and 2 hydrogens bound, so that's 3 things. And then 1 lone pair, that's 4 things, and so this is also sp3 hybridized. So I certainly hope that helps. Okay, thank you for watching the video. Do a little more practice, and you should be able to figure out the hybridization of any atom.